Hello, 8th graders. Today we are going into part 2 of our physics unit, and we're going to be talking about distance and displacement and speed and velocity. In our last lesson, we talked about how Newton said that objects are going to continue doing whatever they're doing, either staying at rest or being objects in motion, as long as there's no forces acting on them. So we're going to start investigating the motion part. So in physics, we have to be able to define what motion looks like using numbers, and that's what speed and velocity are all about. But we can't do speed and velocity unless we understand these other two terms called distance and displacement first. So that's the mission for today. The first thing that I need you to do is open up your notebook and go over to the practice side. I have this diagram on my screen that kind of shows the difference between distance and displacement, and I need you to pause this video and answer the two questions on my screen in your notebook. Number one, based on what you can see in this picture, what do you think the difference is? Just inferring from the picture. And then number two, once you've answered number one and you maybe hopefully have something of an answer, I want you to try number two. John throws a ball straight up in the air and catches it. The distance that the ball traveled was 10 meters. What would the displacement be? Please pause the video and try these two questions now. Okay, we're going to come back to your answers in just a minute, and I will tell you what the difference is. But first, I want to talk about some speeds to give you another way to think about the differences that we're going to investigate today. So I know that we usually use things like miles per hour in our society because that's how we measure things, but the rest of the world uses the metric system, and in science we use the metric system too. So I thought I'd go and I'd find some things and show you what their speeds are in the metric units so that you can kind of get a sense for what it feels like. So we use meters per second, and I started off with really small numbers. So your fingernails right now are blasting out of your hands. Well, maybe not blasting, but they're definitely moving. They're growing out of your fingers at a rate of 0.000000001 meters every single second. They're really moving pretty quick. Something a little bit faster, a squirrel, I don't know whose job it was to measure the speed of a squirrel, but it's been done, is almost 9 meters per second. So they can run 9 meters. A meter is about a little close to 3 feet, about like that. 9 meters per second. A little bit slower than that, a Galapagos tortoise, near and dear to my heart. I love the Galapagos. They are pretty known to be slow. They can really turn on the heat and go 1.1 meter every single second, which if you've seen the size of a Galapagos tortoise, it's a kind of a scary thing to see this giant boulder looking thing moving that fast. The next one is really interesting to me. They did tests where they figured out how fast your blood at rest, sitting there in your chair watching this video right now, blood is moving through your heart at a rate of 4.5 meters per second. I want you to appreciate how crazy fast that is for a teeny little tiny blood cell. So your blood cell comes into your heart and your heart squishes it through all the chambers and out into the rest of your body, and it's moving at 4.5. Remember, this is a meter, 4.5 of those every single second. It's really moving really fast. Light, the fastest thing in the universe, moves almost 300 million meters every single second. A bullet, I don't know out of what kind of gun or what kind of bullet, I just Google searched it, 335 meters every single second. And then the Earth around the sun, so you're sitting on a big rock that's not only spinning like this, but also moving around the sun. We're just talking about the moving around the sun part. Nearly 30,000 meters every single second. We're really moving pretty fast. Well, today I want to make the argument to you that our speed may be nearly 30,000, but our velocity is actually 0. So there's a big difference between speed and velocity, which to a lot of people mean the same thing, how fast you're going. Which, yeah, they both sort of mean that. But the difference in physics is pretty important, the difference between speed and velocity. So in order to answer the difference between speed and velocity, we have to talk about what the difference between distance and displacement are, because those two words go into speed and velocity. So let's go back to the warm-up. For distance, now this is on your note side, by the way, distance is how much ground an object is covered. So if you were to take this winding blue line path, little journey through the forest or something like that, your distance are the actual steps that you took to get to your destination. So if you took a winding path, you would count up all your steps to however you got there. But your displacement is a direct line from start to stop. So your displacement is like how far in a straight line from wherever you started are you now. So the person didn't actually walk this green dotted line, but that's their displacement. Displacement is a straight line. So make sure that you have the definition for these two words in your notes. In order to make sure that this is well solidified or you understand the difference in your mind, I need you to now go back over to the practice side. On your practice side, I need you to please answer these three questions. Number one, can displacement ever be more than distance? Why or why not? Number two, can distance and displacement ever be the same? And how? If you say yes, tell me how. And number three, if you're planning a road trip and you want to know how far it is to another city, suppose you have your maps out and you're planning a trip, what would make more sense to think about? The distance to that city or the displacement to that city? And why? Please pause the video and answer those three questions on your practice side now. Ready, go. Okay, so now that we've talked about distance and displacement, let's talk about speed and velocity. So speed and velocity are making use of those two words. We're going to talk about only the positive direction first. There is a negative direction that we'll talk about too, but that's coming up later. So let's talk about speed and velocity and how to calculate it. Back over on your on your notes side, I need you to have down these equations. These are our first two physics equations. We'll have probably somewhere in the neighborhood of 8 to 10 by the time we're done with this quarter. These are just our first two. So speed is a rate. It's how much distance you're covering, that's what's on the top, divided by how much time it took you to do that distance. So this is where the distance part comes in. Remember, distance is the actual path that you traveled. So speed tells us about the actual route, and it's distance divided by time. Velocity, on the other hand, is also a rate. It tells us, though, our displacement divided by time. So after the whole trip is done, and you figure out what is the straight line displacement between where you started and where you stopped, that divided by time tells us our velocity. Now, there's a big difference between speed and velocity besides just these two words. Speed's units are just meters per second. Velocity's units are meters per second, but it also has a direction. So for speed, you would say I traveled 36 meters per second. That would be really, really fast. But I traveled 36 meters per second, and then that would be it. For velocity, though, you'd say my velocity was 12 meters per second south, or 5 meters per second to the left. Velocity has a direction. We'll talk more about why that matters in a little bit, but for now, that needs to be part of your notes. So we're going to do a little practice example problem with these numbers, and we're going to figure out what is the velocity and the speed. I also want to show you a method for solving problems that we're going to use a bunch in physics. So I've purposely picked these numbers because it makes the math really, really simple, because I don't want you to get bogged down in the numbers for this very first one. I want you to see how we're going to be solving math problems in physics class. So here's how we do it. We use something called the guess method. By the way, this is over on your note side still. I need you to make this table that you see on your screen, and we're going to solve for our speed and we're going to solve for our velocity using this method, the guess method. By the way, Mr. Hankla over at high school, he teaches all those advanced crazy physics, and he still uses the guess method too. So by practicing this method, you'll be preparing yourself for high school physics if you choose to take that class. So here we go. Let's solve for speed first. So the G in the guess method means givens. This is where you list the things that you know that apply to the question you're trying to solve. So if we're solving for speed, we're going to need our distance and we're going to need our time from the information that they gave us. We don't need our displacement because that's not part of the speed equation. So I put in my distance and my time into the first box. The U is unknowns. So for this class, we will only ever have one unknown in a question that you might be solving for. But later on, you might have multiple unknowns, like solve for this and that in the same problem or in the same equation. This class just one, but I still want you to keep track of what in the heck is the thing we're solving for. So in this question, we're solving for speed. So I'm just going to leave it as an S. The next one is equation. So I know we only have two equations, it's the two in red on your screen, but later on in physics, when we have multiple equations that we've been using for all sorts of different things, it might starting to get a little confusing. You might be like, well, that equation has a speed in it, and that equation also has speed in it. Which one should I be using? Well, if you're showing me which one you used when you're showing your work using the guess method, it'll help me to know, or help you, if you're making any mistakes. I can quickly see what your mistake might be, and when you're looking back, it'll help you find your mistakes too. So I know it's simple for this one, we only have two equations, but still, we're going to put in our equation. So speed is distance over time. The first S in the guess method is to substitute. That just means plug in the numbers that you know. So we're going to plug in our distance, since we have that as one of our givens, and we're going to plug in our time, since we have that as one of our givens, but we don't have speed yet because that's what we're solving for. So we're going to leave it as an S. So we have S equals 30 meters divided by 90 seconds. The last S is, of course, solve. Just throw it in your calculator and solve. So when I punch it into my calculator, I get 0.33. By the way, for this class, let's just keep it to 2 decimal places, please. We don't need to overwhelm the screen. 0.33 meters per second. Remember, speed does not have a direction. So this is our complete, whoops, you can't see it. So that was our complete unit, just meters per second. Now let's go over to velocity. Same method, using the different information. So for this one, we need our displacement, which is 15 meters west. And let's pause for just a second. Could our distance be 30, and in the same trip, our displacement be 15? Well, maybe you took this winding trip that went around like this, and that winding trip was 30 meters. But a straight line path from where you started to where you stopped might be a little bit shorter. In this case, half as long, and that could be 15. So our displacement could be less for sure. So we got 15 meters, and we apparently went to the west, and our time is 90 seconds. So our unknown is our velocity. The equation, of course, is displacement divided by time. When we substitute, we're going to put in our 15 for the displacement, and it's the same trip, so it's the same time of 90 seconds. So 15 meters west divided by our 90 seconds. When I punch that into the calculator, I get 0.25 meters per second, but this one has a direction. So because our displacement was to the west, our velocity is to the west. 0.25 meters per second to the west. All right, now it's your turn to do some practice questions. This is going over on your practice side. If you could please label it practice with the number. I'm going to scroll through the screen, pause the video in between each question as you work. So for the first one, these 3 students are off to their different classes, and I want to know who is the fastest runner. The first thing you should be answering in your mind is, should I be using speed or velocity if I want to compare how fast the runners are? Please pause this video and attempt this question. When you come back, I'll show you the answers. All right, if you're still watching, you ready for the answers? Here they are up on your screen. It doesn't make a lot of sense to use velocity for this type of question because we're comparing the runners to each other in terms of how fast they can go. Whichever direction they're running doesn't matter. If I run north and you run south, it doesn't change how fast we're running, or at least it shouldn't. So speed makes more sense for this kind of a calculation. So pause the screen, or pause the video and inspect the screen to make sure that you have the right answers on your paper. All right, practice number 2. This one is a little bit tougher. If you are in an honors class, this is a required question for you. If you are in a regular grade level class, I strongly encourage you to try it, but if you're struggling on this one, know that this one is a challenge type of question. So pause this and give this one a shot. Here's your hint before you get going. You will need the triangle for this one. You're going to be using 2 different steps. So in case you can't remember how to use the triangle, if you want to solve for time, you would cover the t and you would do distance or displacement over speed or over velocity in order to solve for time. Pause this video and give it a shot. All right, if you are back watching, you are ready for the answers. In order to solve this type of a question, here's what you would have needed to do. It gave you the distance that Wile E. Coyote and the speed that Wile E. Coyote had before he got to the intersection. So he had 700 meters to go, and he was going to be going pretty fast, 18.5 meters per second. The Roadrunner, on the other hand, all we knew for the Roadrunner was how fast he was going. We didn't know how far he was from the intersection. And that's what we were trying to figure out, is how far did Wile E. want to start before he lit his rocket in order to crash into the Roadrunner. So we wanted to know how far the Roadrunner was going to be. So in order to solve that, here's what we had to do. The first step was to figure out, well, how much time is it going to take for Wiley? Since we know his distance and we know his speed, we can figure out how many seconds it's going to take. So we would put in velocity or speed is distance over time, plug in the numbers that we know. When we solve, we get 37.84 seconds. We know how much time it's going to take him to get to the intersection. Well, if that's how much time it's going to take him, it better be the same amount of time for the Roadrunner if we want them to crash. So the second step was to take that time we got for Wiley and plug it into the equation for the Roadrunner. So we know the Roadrunner's speed is 8.3. Plug in that same time and we can solve for the Roadrunner's distance, which turns out to be 314 and some change meters. So I want you to be thinking about why, you may even have already asked this question in your mind, why would we care to have two different ways to measure how fast something is going? Well, the setting would really determine when you would use speed versus velocity. I found an example of a time where you would want to use both. So in the military, if you were on a Navy ship out somewhere in the ocean and you needed to fire a rocket to hit some faraway target, you need to know speed and velocity of your rocket in order to communicate with your troops. So for example, your rocket goes up and makes this arc. So the rocket is taking a curved path, but if you were watching it on a radar screen, it would look like the rocket is just moving in a straight line, straight to its target. So if you're communicating to your troops on the ground, like how much time they have to get out of the way or whatever, you would probably want to use the velocity equation to say hey, this rocket is going, I don't know how fast rockets go, 200 meters per second northeast. That'll help them figure out how much time they have to get out of the way. But if you're trying to figure out how much fuel to put in the rocket, then you're going to need to know the speed equation, because you want to know the actual path that it's taking, and the fuel and the fins and the cone shape and all that stuff will matter for how fast it's going when you're talking about speed. So that's when you might want to know both parts of this type of topic. All right, so now our next topic. We've talked about speed and velocity. Now let's talk about average speed and velocity. So your job for this part is to be able to calculate an average. Well, I've noticed that there's a really common mistake when people are thinking about an average. And I want you to consider this kind of a problem to help you understand the mistakes sometimes people make. So let's say that you went on a little trip. Really little. You walked and you rode a bike for the two parts of this trip. For the first part, you walked at 1.5 meters per second, but you only did that for a minute. So that's this little blue part to represent your walking part. And then you, found a bike along the way, 1 minute into your trip, and you're like, hey, walking is for chumps. I'm going to ride this bike. So you get on a bike and you ride for 59 more minutes, and on your bike you ride at a leisurely 5 meters per second. So if you wanted to find the average for this trip, I want you to think about how you might do that. Remember, an average is take all the things, add them together, and then divide by how many things. Think about how you might do this. The mistake that sometimes people make is thinking this: well, since there are two parts of the trip, maybe I'll take the average speed by saying 1.5, since that's how fast he was going when he was walking, and add it to the 5, since that's how fast he was going when he was biking, and then divide by 2, since there were two parts of the trip. But here's the thing. If you do that, you're not going to get the right answer, because the first part of the trip is so tiny compared to the last part of the trip. When you average the two numbers together, it doesn't take into account the fact that the two parts were so different in size. So we need another way to find an average speed or an average velocity. Here's how we do it. In order to find the average speed or velocity, you have to take the total distance divided by the total time in order to get an average. But otherwise, these two equations are basically the exact same. All I did was added in the words total. So let me give you an example. Let's say I walk 100 meters and it takes me 80 seconds. Then I keep going on my bike for 650 meters for an additional 200 seconds. We're going to find the average speed for this. So our equations are on the left. There's a question again. My average speed would work out like this. I would take my 100 meters from the first part where I walked, and I would add it to the 650 meters where I rode my bike to get my total distance. Same thing for my total time. I'd take the 80 and the 200, add them together. Once I've done that, I get 750 over 280 all I do is throw it in my calculator and I find out that my average speed for this trip was 2.68 meters per second. So make sure that this example, as well as the average speed and velocity equations, show up on your notes side. Pause the video if you need to add the equations and the example to your notes. All right, now we need to go one step further. I told you a little bit ago that we were talking about positive velocity. Well, there's also such a thing as negative velocity. And it has to do with this idea called frame of reference. So here's the reason why positive and negative directions exist. So I want you to think about, like, if you're a physicist and you need to define everything in terms of motion, how do objects move? Your job is to define everything using just numbers. You can't use the words up or down or east or west or anything like that. So in order to solve that, what physicists do is they use positive and negative numbers. And it depends on the direction. So if something is moving this way and you've defined that direction as the positive direction, then things moving this way have a positive number for their velocity. Well, if things are moving that way then, if that way has been defined as positive, then that way must be the negative direction. So anything moving that way must be negative. Well, it gets kind of complicated. Let me show you how. In real life, we have 3 dimensions. You have what's called the x direction and the y direction going towards you, and then the z direction going up and down. And each one of those directions has a positive and a negative. So if you have some object that's moving at a goofy angle, it's going to have a positive or negative x, a positive or negative y, and a positive or negative z component. So just one moving object moving at a constant speed is going to have 3 numbers with 3 signs associated with it. You can see how this might get a little bit complicated. Well, for this class, fortunately, we're just working in a single direction. In high school, you might work with an x and a y and think about things on a flat surface like a table. But for this class, we are just working with one direction. So on your note side, here's how we're going to define things for this class. Things that are moving away from your observation or your person, your point of reference, we're going to call those things positive. And that's because their displacement is increasing. So if you look at the little cars on the image, because as time goes by, those cars' displacement, remember that's how far you are from the starting place, is getting greater and greater, we're going to call that the positive direction. Also, if ever things are moving to the right or up, we usually call those positive in physics too. So flip that around. If the cars are moving towards the person of reference, towards you or wherever you've decided to set your point of reference, then those things we're going to call negative because the displacement is decreasing. Your displacement is getting smaller and smaller. So we're going to call that a negative direction. Make sure these 2 definitions are in your notes. Also in your notes, for sake of simplicity, like I just said a minute ago, we're going to usually use the positive direction as meaning up or to the right. And then same thing for our opposite thing for negative. Negative things are usually down or to the left. So I wanted to show you how this can get more complicated. So in high school, you might deal with problems like this. Imagine you took a ball and you threw it way out away from you. Well, if that ball was both going up as you threw it and away from you as you threw it, it's going to have 2 different velocities, an up velocity and an away from you velocity. And those 2 velocities as it flies, because of gravity, well, at least the up and down one, that one's going to change. And so in physics for high school, those are the kinds of problems that you're going to deal with 2 different directions at once. If you go on to physics at a higher level than that, then you might be dealing with all 3. So think about this. As the sun moves through the galaxy, yes, the sun is moving. It's kind of dragging all the planets with it. So we're sitting on a planet where we're not only going around and around like this, but the planet is moving around the sun. So we're basically making little spirals as we go around the sun, but also the sun is moving through space. So we're making little spirals as we move around the sun, as we move through space. That's a lot of velocities happening at once. And it gets really, really complicated, especially if you're standing on another planet. Imagine watching Mars from the surface of Earth and trying to track its velocity as it moves through the galaxy on the spinning planet, going around a star. Imagine trying to hit Mars with a spaceship to land people on it, now you can say why people say things like, well, it's not rocket science. Rocket science can get pretty complicated pretty fast. Fortunately, we're just dealing on the X dimension for now. So over on your practice side, please, take a moment. I want you to write down the answer to these two questions. What is frame of reference? What does that mean? And why does it matter in physics? And then number 2, what does it mean if a car has negative velocity? And is it negative for everyone? Like, think about where you could stand and watch that car. Is negative velocity always negative, or does it matter? Pause this video and explain those two answers. Ready, go. All right, back over on your practice side, we're going to do 2 more practice problems. You've already done 2, so we're on question number 3 technically. A driver drives north for 10 miles for 20 minutes, takes a right, drives east for 10 more miles for 20 more minutes, stops at the grocery store, then drives back to where he started, the same distance in the same amounts of time. I want to know what was his average speed and his average velocity. I've already sketched you a little picture. Anytime you do a physics problem, you should always have a sketch with it too, especially when you're dealing with directions, because it's going to help you to keep track. So the red part was the first part of his trip. The green part was the second part. At the end of the green arrow, pretend there's the grocery store there. Then he got back in his car and he drove back the other way. For the amount of time that he spent at the grocery store, we're just talking about his driving time. So you can ignore how much time he spent at the grocery store. Pause this video and give those a try. All right, so if you're still watching, you've paused, you've tried that question. For the speed part, we have to figure out his total distance first. So he went 10 up and 10 over, and then he came back. So his total distance was 40 miles, and his total time was 20, 20, 20, 20 to go out and back. So 80 minutes. When we calculate that all up, we're going to get 0.5 meters per second. His velocity, though, because he started and stopped in the same spot, his velocity is 0 because its total displacement was 0. And so when you have 0 velocity, there's no direction, because 0 can't have a direction. You can't have nothing to the north, nothing. It would actually be 0 in every direction. So we don't put a direction when it comes to velocity. If you are in an honors class, or you found that to be especially easy, I'd like you to pause again and try this challenge question. If the driver had a speed of 20 meters per second over a distance of 25 meters, how long did it take him to drive? Pause this, give that a shot. Ready, go. All right, for question number 4, this one's a little bit more complicated because we've got a few more turns involved. But there's a really common mistake that I'm trying to see if your brain can work around, and if it can't, I want to make sure that you see it so that it can in the future, that you learn from it. But there's a really common mistake that sometimes gets made here, and I want to see if you can see it. So here are the 2 things that you need to do. What is the displacement, the distance, and time? So kind of set up your equation first, if you're starting at this star and ending at this star. And then, of course, calculate the speed and velocity. So pause this video and give that a shot. Ready, go. All right, so let's talk about some answers. So for displacement, if you started at this star and ended at this star, this little loop that we made up above, the up part and the down arrows, they kind of cancel each other out. So if I go up and then back down, I haven't changed my displacement at all. So we're going to kind of ignore the up and the down part, and we're going to go, it took us 10 meters to get to this part, and it took another 10 meters to get to the final star, so our total displacement is 20. The distance, though, the actual route that we took, was 5 plus 10 plus 5 plus 10, so we have 30 meters total for our distance. The time works the same way. It took us 20 seconds for this first part, plus another 30, plus another 10, plus another 30, so that is 30, 60, 70, that's 90 seconds. Now we can do some calculations. So for calculating the speed, we have to do our total distance divided by time. So here's what we're going to get, 30 meters divided by 90 seconds. And that works out to 1/3, so 0.33 meters per second. Now for the velocity. This is where sometimes people make the mistake. For displacement, we of course have 20, but the time is still 90. If you thought that the time might be 60 seconds, I think I know what you were doing. You were thinking, well, since we ignored this arrow and this arrow for the distance, we're going to ignore the time too. You just kind of completely chopped out those arrows. But remember, even though our displacement is this imaginary space right here of 10 meters, we still actually took this little loopy path. And so the time for that part figures into both the speed and the velocity. It's going to be 90 seconds for both because the time doesn't change. That was our trip. The distance and the displacement might change though, because those trips were different. So be careful about that. So 20 over 90 is your velocity, which works out to 0.22 meters per second to the east. Last one. I'm running late for school and I run 20 meters in 4 seconds out to my car, but I drop my keys along the way because I'm such a klutz. I had to run back 5 meters to pick them up, and that takes me another 5 seconds. I want to know what's my velocity when I first ran out to the car, and then what's my velocity when I went back to get my keys. So it's 2 separate velocities, my velocity out to the car and my velocity back to get the keys. And then what's my average velocity? Pause this video and try it on your practice side. If you're still watching, it's time to check some answers. So for the first part of my trip, I ran out 20 meters in 4 seconds. That would be a positive 5 meters per second. The positive part tells me my direction. You could have also said to the right. That would be fine too. For the second part of my trip where I went back to get my keys, I did 5 meters in 5 seconds. Well, because my displacement was a -5, I went back the other direction. We're going to have a negative velocity. So 5 over 5 is 1, but in the negative direction, so -1 meters per second. The negative part tells us our direction. But you could have also said to the left. Now our average. Hopefully you did not take 5 and -1, add them together and divide by 2, because that would not get you the average. We have to figure out our total displacement divided by our total time. So because I went 20 out and came back 5, my total displacement is 15. I went from the beginning over at the beginning of my red arrow to when I picked up my keys, 15 meters away from the start. But the total time was 9 seconds. So displacement was 15, total time was 9 seconds. So my displacement average, my average velocity was 1.67, if we round it, please round it, meters per second, and I left it positive, or you could say to the right. All right, now it is time to go and get some individual practice. That is going to happen in the Google Forms that I left in Google Classroom. It's called the Unit 1 Part 2 Practice Problems. At the end, it's going to show you all of your answers, so you can go back and check. Please be very careful about units. You're going to punch in the number separate from the units for those questions, and make sure you draw a picture and use scratch paper and a calculator as you go. I'm going to be using this form to figure out which kinds of small groups I need to pull when we meet in class next time. Please pause this video, go and try those, and come back for our exit ticket. Ready, go. All right, if you are still watching, that means that you have finished the Google form with all of the independent practice questions. Now it is time for the exit ticket. Last thing that's going on your practice page before you take a picture of it and turn it in on Google Classroom are these 2 on your screen. Please pause the video, answer these 2 on your paper, and have a great day.